So in this video we're going to show an example of using completing the square to resolve an integral using inverse trigonometric functions in an example where the leading coefficient isn't a 1, so a little bit more complicated than the previous example. So I'm going to go ahead and rewrite my integral 1 over the square root of x minus x squared. And underneath that radical sign I have a second degree polynomial. I have 1 over the square root of a second degree polynomial. Here I have the formula for 1 over the square root of a squared minus u squared. And because that leading coefficient on the x squared is a minus 1, I have a shot at getting it into this form so that I can use the arcsine function to integrate it. So I'm going to go ahead and write the integral of 1 over, and it's going to be the square root. And then I want to do my completing the square. And it's probably easier to take the x minus x squared off to the side and do the completion of the square as kind of scratch work off to the side instead of dragging the work underneath the radical sign. So I'm going to step over here and just complete the square. So I'm going to rewrite it in descending order. So minus x squared plus x. I can't complete the square because I have a negative 1 as the leading coefficient and I need a positive 1. So I'm going to go ahead and factor that negative sign out. So negative x squared minus x, and leave some space for completing the square. Now I have that leading coefficient of 1. So I'm going to complete the square by taking the linear coefficient, which in this case is a minus 1. We need to take half of it, so I'll divide it by 2 and then square it, which is going to give me a 1/4. So to complete the square, I'm going to go ahead inside the parentheses, and to the x squared minus x, I'm going to add that 1/4. We want to notice because of the minus sign outside of the parentheses, I really haven't added 1/4 because when I distribute this minus sign in, I'm going to get minus 1/4. So to negate the minus 1/4 that I've added on, I'm going to add a plus 1/4 so that they sum to 0. So now I want to write it in the completing the square form. So on the inside, I have x. This is going to be x minus 1/2. That's what's subtracted from x and then squared. So when I multiply the x minus 1/2 squared out, I should get back x squared minus 1x plus 1/4. That would be your check on the work. Plus, I want to recognize that 1/4 can be rewritten as 1/2 squared. So using the fact that addition's commutative, I could write this as 1/2 quantity squared minus the x minus 1/2 squared. And that would go underneath the radical sign. So I'm going to get a 1/2 squared minus an x minus 1/2 squared, and right now it's dx. And now I want to notice that it's almost in that a squared minus u squared form with a equaling 1/2. If I wanted to get it exactly in this form, because I didn't feel comfortable working with it like this, I could do the u substitution and let the u substitution x minus 1/2. And if I do that, I'm going to get du dx equals 1, or in other words, du is the same as or equivalent to dx. So now I can make my substitutions. I could say this is going to be 1 over the square root of 1/2 squared minus my u substitution minus u squared. And dx can be replaced with du, and now I have exactly the form that I see here. So I can go ahead and integrate it. I'm going to get the arc sine of u over a, but a is just 1/2, plus a constant of integration. So I'm going to get arc sine of u divided by 1/2 is actually going to give me a 2 times u, but u can be replaced with the u substitution was x minus 1/2. So replacing u with x minus 1/2 plus c. And then we could probably distribute this 2 in to clean things up just a hair. So I'll get the arc sine of 2 times x minus 1 plus a constant of integration.